One thing I always like to remind mechanics, especially your younger guys, and you're looking at the wiring diagram. I know personally when I was a baby learning this, I had struggled with this when I was in the Army. Wiring diagrams are drawn. I don't care who the OEM is. This is when the angels sang when I heard this. I mean, the angels sang, the skies opened up, and I got it. Drawings are drawn in the de-energized position. They are off. And so you as the mechanic, you as the technician, you have to energize the circuit in your head as you're running through with your meter and looking for the circuit. Normally open when it's off, And when I energize that coil, it closes. I turn it on, right? It's normally closed. When the circuit is off. And so to me, that was like the epiphany. And I was like, yes, run around the streets naked going, I get it.
Welcome to CO2 Experts Live. Super excited here, having the top CO2 experts from around the world. Now, what CO2 Experts all about is uplifting the refrigeration industry, technical training, deep dive and troubleshooting. So you as a technician in the field, an engineer in the field, can get some quick tips on how to troubleshoot CO2 systems. Today, I got a special guest, my good friend, Rusty Walker, one of the top CO2 trainers from around the world, trained tens of thousands of people over the years. And we have the pleasure of walking through CO2 electrical wiring diagrams today. Rusty, welcome to CO2 Experts. How you doing, brother?
Very good. Glad to be out here so early in the morning.
Yeah, I'm so happy that you're here too, because we're going to be diving into some good stuff today. Why don't we kick it off? We know we're going to be diving into CO2 troubleshooting. We only have 30 to 40 minutes and we want to do some deep dive. So Rusty, I'll let you kick it off right away.
So I love this screen to begin with because we have this conversation all the time. Is it an electrical problem? Is it a mechanical problem? And we actually get into, no, it's this, it's that. And so we have to understand that there's a marriage between electrical and mechanical. And I'll go through a little bit of that later on. And so like any language, when I learn a new language, I have to learn the verbs and the nouns, and I have to learn how to speak that language. And so when I'm starting to talk about electrical, I have to understand electrical wiring diagrams. I have to understand the symbols. So when I'm turning something on and off, I have to know, is it a light bulb? Is it a solenoid? Is it a switch? What is the component? So I have to understand the electrical symbols that tell me what it is. So here's a couple of them that I thought were pretty important. You can see I have a relay. We use so many relays and contactors. So this is a magnetic coil that's going to energize for me to do some type of work. And that means I can have a normally open contact that I close to turn something on, or I could energize this and take this normally closed contact and I can open it and turn something off. This is a double pull single throw switch. This is just a toggle switch. It's simply, I've been on systems where guys gone through it and forgot to check the switch. Is it on? Right? Here's a momentary push button. I may have a pump skid where I have a temporary alarm and I just want it there until you see it, then you push the button and it's off. A simple fuse, it's a straight line. I have a high pressure. If I don't know if it's open on rise, if it's closed on rise, how am I going to troubleshoot the system? I have a time delay by this little diagonal line here. That's a time delay. I'm going to look on the drawing. How long has it been time delayed? Is it a 50-second? Is it a 2-minute? What is the time delay? When I'm looking at pressure switches, you're always going to see these domes. Well, I have to understand that. So before I even start to troubleshoot electricity, I really need to spend some time understanding the symbols. We use basically the same, but every vendor may use a little bit different symbol. Look at the legend, figure out what he means and what is that? Is it a solenoid? Here's an example of a solenoid that has a light on the solenoid, and I have a panel light. So I have two actual lights when the solenoid energizes. And of course, there's always the all-important grounding link. We have to know where the grounding link is. We have to make sure things are properly grounded. And I love the fact that they drew a little ground thing here, right? So it's showing me that the rod is put into the earth. Earth is ground. Always remember voltage. When I'm troubleshooting electricity, always remember voltage is trying to return back to source when we're talking about control circuitry. And there's so much much of our systems, we're not talking about motors and that. We're talking about a 208 circuit, a 110 control circuit. Always remember, it's kind of like water if you want to think of it that way. But electricity is always trying to return back to source where it was generated, right? And we'll kind of cover some of that. No matter what electrical book you open, no matter what basic book you open, you're going to see my hero, Michael Faraday, and you're going to see magnetism. Because think about that. If I take copper windings, run around an iron core, I create a electromagnet. I turn it on. Do that in the basement. Go into your garage, grab a little iron core, wrap some windings around it, pop on some voltage, make sure it's grounded and it's not conductive, and look at the magnet, put your amp probe around it and look and see that you're going to read the intensity of the magnetic field. Anybody, if you've ever done Ohm's law and you say we represent current with the letter I, the I stands for the intensity of the magnetic field that we're reading as electrons are passed through a wire. That copper wire, as we're moving these electrons, this is the same thing. It's electromagnetism. So let's keep that in mind when we're troubleshooting this, because it's going to be important to us. And I'm going to show you other things I want you to think about with magnetic fields and transformers as we go through here towards the end. A magnetic field, I'm going to pull up. If you ever look at an ice cube relay and really look at the side of it, you can actually see the armature when you energize it. And that's just small armature coming up and touching contacts. And so I have to understand how that works, right? That's pulling it up when I energize pins 13 and 14 on the relay. Transformers, this is a function of magnetic fluxes, but we have multi-taps. How much of the windings am I going to be using? How much of this transformer? So by having a multi-tap, I have a single core and I have different taps off of it. And based on how much of that core I use and where I tap that wire is where I'm stepping down my voltage, right? And so that's what we call these. We all have a multi-tap transformer. Tapping it. I'm tapping it off the coil of that transformer. And so that's what we mean. If we look at the poles outside our houses and we see those massive transformers stepping down 17,000 volts to 240, however I tap that transformer, the windings I use creates the step down voltage that I want to use. All right. And I got to give props I gave props earlier to my man, Michael Faraday. He's the one that came up with this. He was actually one of the few scientists that Albert Einstein had his picture up. Where we have Einstein's picture up, Einstein had Faraday's picture. And by the way, for all those people say you have to have a degree to work on this stuff, Faraday didn't have any of it, and he's probably one of the greatest scientists we've ever known. So just giving him a little bit of props. So here you can see my coil voltage. That is what turns this thing on. Then I can see this is my base. This is the input, if you will. This is going to be 9 to 1, normally open, 9 to 5, normally closed. So I can do with this one transformer or this little relay, you can see I can do multiple tasks. I can wire this one normally open. I can not wire this one normally closed. So I energize the coil. I can turn this on and this off. So when I'm sitting there troubleshooting this and thinking about relays, understand it's not a single function. It doesn't have to be a single function. And so we need to remember that. And remember, the voltage here, maybe 208, maybe 24 volts DC, maybe 24 volts AC. That's important for us. Don't do like me. I was troubleshooting a circuit one time in my own training room. I had a relay bad, and like every other mechanic on the planet, I had it bad. I'm just going to get the relay next to it. I'm going to pop it in just to check and see if the relay is good. So I do it, and I pop it in. I go, oh man, 2 bad relays in one little circuit. This is stupid. And then I grabbed the third relay because the engineers and the OEM who put it together, they're just stupid. And so I popped the relay back in. This time I see the magic smoke leave. And I looked at the coil and went, oh, I just popped in a 2 24 volt DC coils into a 110 volt base. Yeah. So make sure you're focused on that, because you can let the magic smoke out. And so just make sure when we're looking at these, we're checking the voltages. Make sure we're looking at the coils. When we're looking at transformers, make sure we're focused on how many VA do I need? Is this the right VA, the volt amps? Is it big enough? Is it big enough? All right. Here, I told you right here, you can see the common pin. There you can see the normally closed and then normally open. It's barely open, but when I hit this coil voltage, that's going to energize and pull this armature down and switch over to the normally closed side of that coil. So if for those of you who've ever wondered how these look, and you can actually pop them out and look at them, and you can see you can look like a fuse and see if the filament voltage is there. And so I just thought I'd share that with you because I don't know how much we do. And I'm
So
telling
Rusty,
you, dude,
just go back to that. So explain it just one more time for the new people. So when it goes from when it's not powered, you got no power to your coil, 921, which is the top one, is normally closed, right?
and you can see that here.
Yeah. And when you
And then
energize it, that white box that's in there, there's a coil under there. You can't really see the coil, but that there's a coil, there's wire wrapping under there, like Rusty talked about earlier. When you put power, AC, DC, 120, 240, that magnetic field pulls down that little armature and it magnetizes it. And then just like Rusty said, 9 and 5 now are closed.
and I appreciate you saying that because one thing I always like to remind mechanics, especially your younger guys, and you're looking at the wiring diagram. I know personally when I was a baby learning this, I had struggled with this, and when I was in the Army, wiring diagrams are drawn. I don't care who the OEM is. This is when the angels sang. When I heard this, I mean, the angels sang, the skies opened up, and I got it. Drawings are drawn in the de-energized position. They are off. And so you as the mechanic, you as the technician, you have to energize the circuit in your head as you're running through with your meter and looking for the circuit. Normally open when it's off, when it's off. And when I energize that coil, it closes. I turn it on, right? It's normally closed. When the circuit is off. And so to me, that was like the epiphany.
Yeah.
And I was like, yes, run around the streets naked going, I get it.
No,
So,
exactly.
well, maybe not that far. Sorry. You didn't need that image. Just keep understanding. And relays are so important in our circuitry. We have them everywhere. These are the precursors to 8RO boards, multiplex, 205, 204 boards, our relay output boards, right? We still have these. I don't have to run through the program. They can still do programming-ish things with these relays. And when I say they're everywhere, I mean they're everywhere. This is on a CO2 cascade overfeed system. Simply look at the relays here that would turn the cases off, right? And so you have to understand this logic in order to troubleshoot this. This is one of the most confusing system for guys who don't understand it. And I get phone calls on this all the time. By the way, if anybody ever calls me with an electrical problem, I'm glad to help anybody and everybody. And I can work on now with the NASRC, I can help everybody. But if you have an electrical issue and I ask you what voltage you're reading and you tell me the meters in the truck, the next thing you will hear is the busy tone or the phone tone because I'm hanging up. Don't always bring your meter in with you. Always bring your meter in.
And get
So
the
I
electrical
thought
wiring diagram too, right? Get that
what's that?
before the electrical wiring diagram. Make a phone call to the manufacturer, get the diagram. It should be at the rack somewhere. If you're not reading these every day, you're not going to understand how to troubleshoot electrical. That's it. Because every system is a bit different. So you need the wiring diagram, because you can call Rusty up and say, listen, I have this circuit here. It's the control circuit, or it's the compressor circuit, or it's the condenser circuit. Here's my points. Here's the voltage going down. There's this transformer here. I'm not reading the right volts. And it could be like someone just added another controller on it and you don't have enough VA to open the electronic valve or not, but you need the wiring diagram to troubleshoot this stuff.
The OEMs are happy. If you call the OEMs because you can't read the diagram because you're working on a rack that's been there since 1980, try to find it. And what you really want to do, your goal is, remember, 85% of our service calls are electrical in nature. So it's important for us. And with CO2 and A2Ls, it's going to amplify. It's going to be exponentially greater. So we have to get it. So I always say this: if you want to get good, if you want to be a great mechanic, study your electrical drawings, look at them, practice drawing them. I always say a mechanic should be able to draw. I should be able to give you that circuit, and you should be able to wire it to some degree on your own. right? That's your
100%.
goal. That's who you want to be. You want to be that guy who can start laying it out. And I'm telling you, if you're the dog that can read electrical when nobody else is, you're the dog. You're the main dog.
100%.
So I'm going to do a real quick sample diagram for you. This, and then we're going to get into a more complex one. And I'm going to go into a little bit more. So you can see right here, I have L1 coming here, L2 here. There's a 208 circuit. So I have, this is L1, my red leg. This is L2, typically black. So when this controller, this is a Corel controller, a Form A contact. He says, okay, I need the condenser fan. So he's going to close this relay. That happens at the controller in the logic. We're going to talk about that in a little bit later. Close that. That simply means I'm going to close that. I'm going to energize this. That means if for this to be energized, I should have voltage here and here, 208, right? When that energizes, that is going to open this set of contacts, yes? That set of contacts are going to open, actually turning off the condenser fan. This is kind of backwards because they're not using a Form C contact. They're using a Form A. So they actually had to add this relay to open this to turn that off. Now, you look at this drawing, I'm hearing you guys right now going, well, that's stupid. It doesn't matter if it's stupid. Troubleshoot the drawing in front of you. You know, I hear people say all the time, well, that's not so-and-so does it. You're not working on so-and-so's rack right now. Troubleshoot the drawing in front of you. This is how this system is done. Troubleshoot it. Understand it. To turn this off, I actually have to close this. All right. So let's look at the same controller, or this is the same controller. And this, they only have Form A contacts. Form A versus Form C. Form C has a common and a normally open and a normally closed. Now, Form A simply has a common and a normally open. You can't make that decision. You can't wire it normally open or normally closed. So sometimes you have to use your relays to finish out the logic. All right. So let's see what we're going to do here. Split condenser. If I close that, that's going to energize the split condenser valve relay. Okay. So what's that going to, is it going to turn it on or turn it off? I have no idea yet. So then I go, the split valve, CPR7, always notice CPR7. The OEM is going to tell me if I have a coil called a relay, a contactor, and it's labeled CPR7. Turning a coil on by itself does nobody any good. I have to go find it. It may be later on that page. It may be 3 pages over on the wiring diagram. It just depends on how it's laid out. So I have to go find CPR7. I find CPR7. It is a normally 9 and 5, normally open. We close that. Remember, we said 9 and 1 is normally closed, 9 and 5 is normally open. We close that, and we actually just put it into split. Good? Is everybody good with that? And remember, L1, L2. Doesn't matter if it's 110 or 208, 240. All right. And we're going to get to that in a minute. But that's a simple little circuit. But it shows you how we're using relays to complete the computer's logic. And how if I didn't understand that, or if I got whiny, or if I just was looking at it and go, well, that relay closed, the solenoid should energize or de-energize. Wait a minute. Look and see what the logic tells me, and then follow it through with your meter. Follow it through. You're the most important tool you have in your toolbox. As far as I'm concerned, 85% of our service calls are electrical in nature. Our most important tool is our meter. And yes, I've been converted. I am now a field piece guy. I hate to tell you old guys, but I bought my first field piece. I'm in. I got it. So my flukes are getting rusty. Ha ha. Rusty.
Yeah. I got it. So this is so important, right? So you got to get into the wiring because it could be 4 pages down too. Like when you're looking at a big system, there might be multiple pages. So you got to follow what it says. It might say, okay, go to page 4 or page 6, or it might have a special symbol on it. But you got to spend the time in these different manuals because every manufacturer is going to do a little bit differently to do the same thing.
That's exactly right. And a lot of times they just don't tell me where the contact is. Let's look at this one real quick. This is on a overfeed system. I love this drawing. I love it because I understand it.
Yeah.
Right? When I first looked at it, I went, what the hell? But I understand it. So now it's easy for me. Right. So I'm going to give you a couple of hints before we get too far. And the thing to understand is, remember, I'm trying to turn on whatever's on the right side of this drawing. That is my goal. And so PSC1, pump shutdown control relay. I'm going to give you a hint, and we're going to see this on the next page. If PSC1 is not energized, neither pump was be on. So if I walk into this motor room, or somebody calls me and says, hey, I'm on this overfeed system, I can't get either pump to run. Neither pump is running. Well, you just told me part of the problem. PSC1's not energized. Well, look at all of these safeties that are in that circuit. So any one of these safeties can turn this on. So I'm going to go. Some of you guys are going to get a little irritated with me here, real quick, but I'm going to preach gospel here. So a lot of you, first of all, L1, L2. All right. A lot of people want to go from here to ground, unless you're looking for a short. You're reading parasitic voltages. You are not reading a difference of potential. And let me help you break difference of potential down. If I take my meter and I put my red lead and my black lead on L1 on one wire or across a fuse that's good, I will read how many volts? 0. There's no difference of potential in there. There's no energy there. But if I take that black lead and I move it over to 208, now I move it over to L2. I now read 208 volts because there's a difference of potential through there, right? That's how a light bulb works. It's a filament voltage, but there's voltage drop, so it allows that potential to go through. So my light bulb works. So here's the way I troubleshoot. I learned this in military. It's helped me, and I'm telling you, if you guys practice this, it's the best way to troubleshoot a control circuit. So I'm going to take L2. Now on my meters, my red lead, I have a 4-foot red lead. I have a longer red lead. And here's why. Because I'm going to take my black lead and I'm going to come up here to the control breaker, L2. I'm going to loosen it just a touch, and I'm going to slide my black lead under L2. This way I don't have to touch it. I don't have to move it. Now, because one of the things I want to do is I want to try to use one hand as much as I can, because if I'm touching both hands on the electrical panel and there's a short in it, remember, electricity's trying to go to source. So the quickest way to ground would be through me. And so I always keep that in the back of my mind. When I can, I try to use one hand. So if I tie that black lead to T2, L2, then I can put my magnet on my brand new field piece meter, and then I can go. And so PSC1's not working. The pumps are not. So let's do this. So I just tied my lead to T2, L2. I come up here. Let's just make it easy. I'm going to pop it here. I'm going to put my meter right here. I have 0 volts. Well, it's probably not this coil. He's not getting voltage. That means something along this path has killed my voltage. So I'm lazy. Be lazy, because when you're lazy, you use your head more. And so I'm going to look at this circuit. I'm going to break it in half. So I'm going to go. That NRO board is right in front of me, in my circuit panel. So I'm going to pop on board 1, pin 7. I'm going to go to the output of that board. It's an easy place to find. Boom. I put my red lead there. I got 208. Good. If I got 208, which way do I go? Well, I don't go that way, because that means that's closed. My pressure's not high, and this output board is closed, because otherwise I would not have voltage. So since I have voltage, I'm headed this way. If I wouldn't have voltage, I would go back this way, probably to this pin here. It doesn't matter. I like to make it easy. I don't want to go component by component. I try to break off 3 and 4 components at a time, because ice cream is melting, and I want to keep that store manager out of my hair. But let's say our circuit, I went here, black lead on T2, my red lead here, 208. Perfect. Now for me, I'm going to go with now I understand the circuit. So I'm going to look at this circuit and I'm going to go, okay, if this relay point is good, easy to find, I'll go here. Okay, for our discussion, I'm going to find 208 there. So now what? I know this relay point. I know this situation is satisfied. I know that relay is closed. All of this is good. Ah, I'm going to go to pin 3 on this relay. No voltage. I had voltage here, no voltage here. I go right here, voltage. Then I go, what is this alarm? This is like 4 pages back where the coil is. It's like 5 pages back where my optic eyes are. But on that page, it says that if that liquid level is open, if so now I know I'm running out of gas. It has nothing to do with the electrical circuit. The mechanical, I'm low on charge, but my electrical circuit took me there, right? And so I know to focus there. Either that relay is bad or I'm low on charge. Just check your liquid, your CO2 level, and see if you have CO2. It could also, remember, it could still be the relay, because maybe this is stuck or this is bad and it's not closing. Although it's normally closed, it's not opening. Or it has opened. You know what I mean. All right. So keep these things in mind. And then that causes PSC to de-energize. Any one of these things causes that to open. All right. And these are just some different alarms. This is an overpressurization circuit, which would take the whole store down. And we would find that in a different part of the circuit. But this also is like 6 pages away. We have to find, I have a coil. That means I have to have a relay point. I have to have normally open or normally closed position. All right, so let's go to the next page. There's my pumps. What is the first thing we see on our pumps? PSC1. PSC1. So I'm using one relay and I'm using one set of safeties to protect 2 pumps. And once you get good at this, then you'll start seeing, man, this is great. And so I'll show you, because I know we're truncated on the schedule, but I do want to show you something else. So if this is closed, everything goes, and I energize, my motor stators are good, and I energize the pump. But when I energize this circuit here, yes, I come up this way on this drawing. Remember, the drawing's a roadmap. It's before we had Apple CarPlay. And so if this starts, that means it's going to produce current around the wire. That current, that magnetic field, is going to be sensed by this current sensing relay, which reads a magnetic field, the intensity of the magnetic field, that will close. It's kind of a proof to tell my pump is on, but it's also going to energize this PRR1. When that energizes, okay, what does that do? I have no idea. So what do I have to do? I have to look at my drawing, and I notice it's a normally closed set of contacts on pump 2. So if this energizes, because this closed, because this started, this is going to what? It's going to open. What did I just do? I just locked out pump 2. I just made sure that both pumps don't run at the same time. So if I walk in, I see this, and then both pumps are running. The first thing I'm going to do is start looking at PR1 and PR2. Maybe the coil is bad, or the relay pins are bad, and I'm actually have both of them closed. Maybe it's wire drawn. Maybe somebody went in there thinking they were doing one thing and they actually did another thing. And so, but I can't get there if I don't read this drawing. Right?
I love it. And that's so important. That's the thing, is understand the equipment you're troubleshooting at that moment. And don't worry about what other systems you were at before. That new system that you're on, think of it's the first piece of equipment you're working on. It's just like doing a service call. Even though you had a service call that may not went so good before an hour earlier, it's a brand new customer. It's a brand new service call. It's new. Take it what you're working at that moment. That's the most important thing, because this next wiring diagram is going to be different than the next one. And like Rusty's saying, take your time on this stuff. Get into these wiring diagrams, because if you don't have this wiring diagram, you're going to spend an hour and a half trying to figure out, where do I start? And with this service call, like Rusty would have walked in here within 15 minutes, he would have known that, right? By using his meter, finding out where the power is, where it's open or closed, 15, 20 minutes.
Understanding the drawing, like Trevor just said, it by taking the time to really understand, and you know, oh, I don't have time. Yeah, you do, because the slower you move, And the slower time you take, the faster you are. To get fast, I slow down, right? Because now I
Totally agree.
solve the equation quicker and I get to the end point faster. So slow is slow is fast. So understand the wiring, study it, be the dude. Be like Trevor. Be the dude, man. Be the guy they call because he was, every day I wake up, I want to try to be the dude. I fail miserably, but I try. So, and this just shows the way. Here's a great one. Here's on a booster oil system using HB sensors. If you walked in and that's all you saw, could you fix it? Could you walk through the circuit? Where would you start? A lot of times that's the question. Where would you start? Well, if I had this compressor off on oil and I knew this was my troubleshooting circuit because I understand the circuit, well, the first thing I'm going to start now, I'm going to go through the sequence of operation normal, then we're going to back up and fix it. All right. So the first thing that's going to happen in the circuit is, for those of you who have worked on these, this is that HB sensor that you use in ammonia all over the place. They use these in Europe. Trevor and I were both just in Choventa, and I saw them all over the place. This HB sensor. It's a sensor, but it's a switch. And if you look at it and look at the model number, it says switch. Okay. So I have the drawing here. 24 volts DC. Oh, check this out. 24 volts DC. This is the same page. 24 volts DC, 120 single phase, 208 control. Pay attention with your meter. If you don't know how to read wiring diagrams, take the selector switch and put it on auto detect so you don't blow your meter up. And it will automatically switch AC to DC for you. But don't be that dude. Be the dude that knows. So here we go. Oil switch. This is good, that means I'm running. But now I need oil. I'm going to close that switch 1 to 3, passing 24 volts DC to this coil. So the first thing I would start, where does the circuit start? It starts with the sensor of the switch. So that's where I'll start, because we're doing the order of operation first. And then what is that going to do? That's going to energize this low temperature compressor oil relay. How do I know? It tells me it's L2 LOR1. I have to read the language. And so that's going to simply close this normally open set of contacts. This is a dry closure. There's no voltage, as you can see here. It simply goes to a digital input board on my controller. So all I've done so far is told the controller which one. I don't care. RDM, Copeland, Danfoss, Microthermo comrades, right? It doesn't matter. It's a digital closure. So then I just told the controller, dude, I need oil. The controller says, all right, well, how about this oil valve control? All right, that's pretty simple. I close that board and point. When I close that board and point, it energizes LTOVR1. When that energizes, well, we already determined there has to be a coil or a relay pin somewhere, a normally open or normally closed set of contacts somewhere. And so let's start looking for L2VOR1. Here we go. Pin 6. Close that. Oh my God, can't believe it. We finally turned the solenoid on to energize the oil. Any break in this circuit was going to cause an oil failure, a mechanical issue. My compressor's off on oil. Why? All right. So now let's say I'm coming into here and all I know is my compressor's off on oil. Where am I going to start? I'm not going to start at the switch necessarily. I'm going to start at the solenoid, because that's what's not coming on to feed oil. So me personally, what I do is I'm going to, again, put my meter on T2 or L2, and and even on DC, I put it on the negative part of the DC. That's a negative voltage. It's not going to be like a neutral or whatever. And so I'm going to go on the other side. It's going back to source, AC or DC, AC and DC, greatest rock and roll band ever. Sorry. But I'm going to go, okay, he's not energized. Why? Where did I open the circuit? Well, being lazy, I'm going to go up here. The relay point, the board is right here in front of me. The electrical panel, it's right there. So I'm going to pop my meter right here. If I have, this is 208, I'm on T2. If I have 208 here, which way do I go? I know the controller said go. I know the controller closed the relay. I'm going this way. If I don't, now do I have a bad relay? Is the fuse bad? Because I check voltage here. It could be the fuse on the relay output board, right? And that's how I would find it. Because I have voltage here, no voltage here. No, I have two questions. Is the controller calling for it? Remember, is the controller calling for it? That's something we get all caught up with, and we're going to cover that in a minute. Listen to what the controller tells me. Is it calling? Yes or no? Right? Is it calling? If it is, that should be closed. I probably have a bad fuse. If it's not, then I'm coming down here to see if I got a digital closure. Is he energized? Because if the controller's not doing what he's doing, maybe I'll check and see. I'd ohm across that to see if I had a closure. If not, I may check right here because the HB sensor simply did not switch from pins 1 to 2 to 1 to 3 and didn't send that 24 volts DC out to energize the coil. So does that make sense to everybody? You just have to think what's supposed to turn on, who's turning it on, and what voltage do I expect to see? Okay. And so when we get there, this looks complicated. And this is something I do. I carry colored pencils with me, learned it from the Army. I take and like if I get something from an OEM, the first thing I do is take out my electrical drawing and I color in my circuits, my black and red wires, so that I can see it quickly in my mind's eye. And I'm a big person. I think Trevor is too. I'm all about visualization, and so visualize your circuit and think about your circuit, and it's going to be easier. I'm telling you. You practice this method, and it's going to get you out of there a lot quicker, and it's going to stop you from going, well, on this switch it's reading good now, and on this switch, stop it. Read the drawing, read the circuit in front of you. And I don't mean to make fun because I do that occasionally too. We really should be reading it here and doing it here. Yeah. Right? Just get good at it. But go ahead, Trevor.
The thing that I want to point out is that we as technicians are always putting out fires and things aren't working all the time. When a system is running normally, this is why I know everyone should do a startup, do a couple of startups. But when the system's running normally, that's when you should be taking your meter out and going along the wiring diagram so you know what it should look like when it's running normally, versus when you go there, you've never been at the system before, or the only time you've been at the system is when it has an electrical issue or a problem. If you don't know what it's supposed to look like normally, then it's going to be harder to troubleshoot that system. So start troubleshooting systems that are running already fine and start using your meter, just like Rusty's talking about, going across and getting an understanding. Should I have 24 volt DC there or not? Is it open? Is it closed?
I like that idea, Trevor. Use your meter sometime when everything's working fine and just do the things we're talking about and see, oh, I get it, right? You've got time. Everybody says we don't have time. You have time. We have more time than we say we do. Believe me, I've been in a van. I know what I'm saying. You guys have more time. All right. So if you guys could just hang with me for about another 10 or 15 minutes, I promise you I'll pull this in the driveway, especially for my American friends who were up late last night. I'll try to get it so you guys can go take a quick nap. So this is the high pressure control valve. This one is the ICMT valve. The ICMT valve, it's used in ammonia all over the place. It's used in bigger industrials, CO2. It's kind of being replaced with the CCMT valve, but it's still, there's so many of these things around here. And so let's see what this thing does. This is the high pressure control valve. It is the one on the drop leg. I've got 24 volts on the red leg, power leg coming into it. Now on the black leg, I have a 0 to 10 volt signal coming from my analog output board. In this case, it happens to be a Danfoss 103, but it could be off of a Dixell controller. It could be off a 326A. It could be off the microthermal, the 744V board. It's a valve driver board. They're all it's an analog signal. It is a stepper, but I like to refer to this as an analog stepper, not a bipolar stepper or a unipolar stepper. And I'll show you why. Because coming right here, you see 17 and 18 coming off the controller. That's a 0 to 10 volt DC signal coming into these two pins off the yellow and green wire. All right. And so if the valve says 50%, it's open 50%, I expect right here to read 5 volts DC. If this says 48%, I expect to read 4.8 volts DC. That tells me the controller's in charge. And I want to make sure, because we want to get, as we do boosters, we want to get in the habit of looking at where the high pressure control valve is versus ambient. And so we want to make sure we're getting a good signal. Let me caution you here, though. There's a lot of people that are not paying attention to these high pressure control valves. How many times have you heard when you're talking about computers, garbage in, garbage out, right? We hear it all the time. Well, in order for the high pressure control valve to work properly, not only do I have to have the transducer, that is an input, the pressure input. I have to have that set up. I also need to make sure the temperature probe coming out of the gas cooler is not only about 6 inches out. I want to put it about 4 o'clock, 7 o'clock on the pipe, but don't just insulate it with duct tape. You want to put thermal paste is awesome, but then wrap it with Rubitex, but then get you a little piece of vinyl PVC wrap. What if you're in Miami? That Rubitex will break down in 6 months. And now I'm not protected. That temperature sensor is very important in driving this high pressure control valve. So we're talking about electrical, but we got to talk about our inputs as well. So make sure you got a good input. Now, let's say the high pressure control valve's geeking out. Here's a little trick I have. To Amazon, I bought me a 0 to 10 volt, small little 0 to 10 volt or 4 to 20, I can switch signal generator. So if I'm not sure, is it the board or is it the controller or is it the ICMT itself? And I can take the wires off of the 326, the iPro, the Dixel, whatever it is, and I can hook my 0 to 10 volt meter up and I can drive the signal manually, and I should see that on the face of the ICMT. And if I can do that, I can say, okay, from pin 17 and 18 on my drawing to here, I'm good. So that takes me back to the controller. That takes me to the wiring of the controller. And so that's some things I think about. How do we use better tools, smarter tools to help us cut the problem in half, right? If I have voltage here, if I hook my signal gen and nothing happens, I'm going to focus here on either the wiring or the circuit board. There's a circuit board inside of there underneath the cover, and it may be simply the circuit board burned out. All right, so I'm going to come here. This is the flash gas bypass valve. These are bipolar steppers. Real quick, I want to go through bipolar. A bipolar valve simply means, we all know how many steps. I don't care how many steps. I really never do care, because a step is a predetermined movement. When the controller, the iPro, whatever, sends a signal to it, it's a predetermined amount of movement that I have on the rotors and the stators to move that valve positively or negatively, right? And so all a step means is the predetermined, unless I'm programming. If I'm programming, I care. But as a technician, I just want to know if it works, right? So I don't care what the steps are. I'm not there to redo. There's like 10 guys in the field that can really understand PID. So if you're not that guy, leave PID alone. Let's look at the voltages. It's more the voltages. But let me show you this. This is something I find really cool and you guys can do. Of course, we can take, if we think the valve is bad, we can take each winding to ground, make sure it's not shorted. We can make sure it's not open by using our ohm meters. But if the rack is running and you don't know if this thing, you're thinking, I don't know if it's the Dixel, the 326, I don't know. And you can take your meter, put it on DC, then take your leads and go to the white and black wire. We're all using white, black, red, and green. That's just the standard. I put my meter here. If the valve is energizing, working properly, and my controller is sending the proper signal, I'm going to either see somewhere between -5 and -3 volts DC. And every time that valve moves, I will see it switch from negative to positive. -3, +3, -3, +3. Now, sometimes it'll go positive. If I'm close to set point, it's not going to send a signal, so I'm rarely going to see that move. And so if I'm suspecting this wrong, I can simply go into the controller, change the set point so that I can force this valve to drive to a new position, and I will see it go -3, +3, -3, and maybe -4, maybe -5, whatever. But I can see it moving. And then I take my lead back to the red, green, and red. And I want to replicate that. I'm going to see the same thing. And if you've never done that and you're at the rack, next time you're at a stepper valve, try it. It works with the CCMT, the CCM, it works with the SCRs. I do it all the time just to prove my theory because it's something you want to see. But think about it. Every time it steps, it's got a signal, and you can read that signal with your DC meter. All right. So that's just a really easy way to troubleshoot and determine if it's the output board, the 208 or the 408 board? Is it the 208C board? What is it? Okay. So, and that's one of my favorite. Back to the high pressure control valve. Look at this. Do you know that this is online? It's called the internet. And if I pull that down, I can take one of those needle leads. Everybody got the needle leads you put on your meter real thin. If I put my needle leads on D and F, so there's a keyway. So I would hold it and look at it, put my leads there. Whatever's coming off the controller, DC wise, voltage wise, 4.5, whatever it is, I can see that on my meter. I just proved the wire. I proved the controller's good, the wire's good. It has to be the circuit board. There's nothing else it can be. Right. And so look at the things and look at some of these things. And when you see these kind of cable plugs, if you go online, you can find this kind of information. And dude, I'm telling you, this has helped me 2 or 3 times. We've condemned 2 and saved 1 by using this cable and reading it through here. All right.
Some of the manufacturers as well is if you got a big industrial rack, it could be 40 feet, and sometimes at the manufacturer, they only have 20-foot length of wire. And so sometimes there's splices. So what Rusty just said there, and I've seen it multiple times, that you got to check that wire because that could have been wired. There could have been a splice in one of the wires going back to the board or the signal wire or the 0 to 10. Our job as technicians, not to get mad at the manufacturer or whatever happened at the factory, is going in and verify, are those points exactly, is the resistance there? Are we getting the right voltage? Resistance, whatever you're looking for, because that stuff does happen, especially with electronics when you're doing runs of 100-foot to electronic valve, not only for this one.
Remember that because you see these butt splices when they put a butt splice in. I never could figure out why you butt splice a white wire to a green wire, but whatever. It's not my place to judge. But we just, as Trevor said, it's our job just to figure it out, cut it out, fix it. Add another $30 to the invoice just for aggravation. Don't do that. Don't say Rusty said to do that. But here's the same thing that I just said, just kind of a bigger set. This is using a CCMT valve. Doesn't matter. White, black, red, and green. It's the same thing. It's just like when we're using our SMA 12. Don't forget your SMA 12. You can use the SMA 12 to drive these. If you're not sure if it's driving or not, just hook it up to your Sportland SMA. By the way, give Sportland a plug. They are coming out with a new one with a unipolar. Danfoss has one. I'm fixing to make my own. Just got one of the guys at Coolsys sent me some parts, and I'm going to make my own. But use those tools. Danfoss makes one. Use a stepper valve driver. We are going to be ate up with electronics. Electronics are not going away. We're going to exponentially. We're almost going to have to be electrical engineers. So we have to get better tools. All right, real quick, and let's finish with this. And this is if I have time, hopefully I can get through this.
Let's do it.
This is not good. All right, if you're doing microthermal, maybe, but everybody wants a daisy chain Modbus signal. That means if I take this point and this point and I pull them, it's a straight line. That's how I know if it's a daisy chain or not. Do that in your head. You can go all over the place, but you have to be able to grab both ends and stretch it. All right. So everything's being daisy chained, right? I keep saying the mechanical expansion valve is going the way of the dodo because I can't log into a mechanical expansion valve. And everybody wants to Bluetooth. Everybody wants to dial from Washington State into the rack in Miami, right? I want to be in Calgary and I want to look at the thing in Quebec. It's just the way it is. So just keep that in mind. So this is important. We have to make sure we understand it. And so here's some modern tools. With Modbus, we're all used to going center to positive, center to negative, reading 2.4, 2.7 volts. We're all used to troubleshooting it. Like, how many times have you been here? Something's going offline and one guy's on one end and you're at the controller and he unplugged. Is it good? It's on now. No, good. No. The other one went off. Okay, wait, here, I'll put this one. No, that one's down. They said this. Dude, which one? Okay. All off now? What the hell? We've all been
Yeah.
I've spent 2 days trying to find Modbus, looking at every single wire and make sure one strand isn't touching. We've all been there. That's so last year. Let's get better. So I want to introduce you to two of my favorite tools. This one is a intensity meter. It reads the intensity of a magnetic field, kind of like an amp probe. But check this out. It reads in microteslas. Why? I don't know. But you can see it's red. I'm reading 290 microteslas. This is my Modbus for a Corel controller. This is a Modbus to USB converter. And they keep dropping these things offline. Nobody can figure out why. What do you see right here? 1, 2, and there's 2 more. They ran it by the transformer. Transformers are hit up with magnetic induction, magnetic fields. So they're running straight through the magnetic field. And if we look on an oscilloscope, which we will, I would see all this noise. So this is I paid $15 for this one. Nice little tool, Amazon. But here's my boy Pikachu. This is my oscilloscope. I used to use these in the Army. He's small. He fits in my backpack. I have a Pokeball for him. And here's how he's going to work. So here's Pika. I have a cable that goes to my laptop. When I bought this, it has software. This software is going to give me a DC signal. I'll show you that in a minute, a square wave. Remember, Modbus is a voltage, a DC signal. We know that because it says 2.6 to 2.4 volts DC. All I'm going to do is read that DC signal. Then I take my probe. I come up here to my controller. This happens to be a Corel Boss, but I've done it with Emerson. I do it with Copeland, and it works Modbus or Lawn. I can do this with microthermal as well. But what I'm going to do is put my meter leads in series, in parallel with my Modbus signal. And so what I'm going to see is, if I run this is a beautiful square wave. Notice the amplitude, see how it's transmitting. Matter of fact, if I hold my laptop up to my controller, where I have that TX and RX light that's flashing, that will flash at the same rate. And so that's a beautiful signal. And so if I go here, that's a horrible signal. The amplitude is too low. There's no transmission and no receiving. So what did we do with this? I want to go quickly on here. This was on 40 cases on one Modbus network. The first thing we did, 40 cases. How the hell are we going to troubleshoot that? Well, what we're going to do is disconnect code case 20 and disconnect 21 through 40. As soon as we did that, the signal came up. We were good. So we just said the first 20 cases aren't good. So what we did, we added 5 more cases. When we added the 5 more cases, the signal went to this. So we knew the problem was between 21 and 25. Then we broke it in half again. We were able, within 40 minutes, find a broken wire in conduit on the Modbus circuit in 40 minutes. 40 minutes, broken wire in conduit. So let's get smarter, use better tools, be smarter with our smart tools. Matter of fact, if you buy one of these, I have 3 subroutines I use that I've already pre-set up. If you send me an email and $100, no, you send me an email and I'll send you my subroutines.
No, it should be.
I'm trying to give it away. And then one last thing, I promise. Remember when we're looking at refrigeration and racks and supermarkets and industrial, it's a marriage. It's a marriage between the piping, the electrical, and the IO list. I cannot troubleshoot a system without understanding the 3 of them work together in concert. All right. They have to work in concert. And I just want to make sure everybody's aware of that. And we have to close that loop. And do I have time for one more quick story?
Yeah, let's do it. Let's do it.
All right. So here's a primary, this is a case controller. Notice these are Form A contacts. The controller closes these relays. Okay. So I want to tell you a place of pure failure on my part. I was so depressed. So I taught a class, basic elect, and I left that class and I'm like, I am cool. I knocked it out of the park. These dudes are ready to go, I'm like, how? And so that was Tuesday. Wednesday, we go into the store for some practical. And we walk in, and one of the cases, lights are off. And this is what I mean by a marriage. And this is what I mean that we have to connect. We have to close the loop. We have to think about critical thinking. We have to process this. We can't just look at a widget. I can't just look at this piece. I have to look at the whole. And here's why. So we walk in and I go, oh, look, case lights are off on case one, an open deck, a multi-deck, 12-foot case. Yay, let's find why the lights aren't. And then we walked up there after a take of electrical. The first thing they started saying is, I'll bet the motion detector's open. Dude, that's not what we talked about. I said, okay, before we do that and try to troubleshoot anything, we don't know what's going on. So it's a Bluetooth case controller. Let's Bluetooth in because Bluetooth is cool. So we Bluetooth into the case controller and we're all in a group. There's like 10 of us and we're looking at it. And I go through there and I go, oh, look, let's go to the digital output. We went to the digital outputs on our phone and the digital output said lights off. Okay. So our original question and problem was, why is the electrical circuit not turning the lights on? But once we saw the controller set off, the question and what we're trying to solve changed. Now we want to know, why is the controller telling us to be off? Two different questions with two different answers, right? But I said, oh, look, the lights are off. I think it's the motion light. No, it's not the motion. What about that relay? Somebody get a meter. Let's check the relay. What relay? The relay out here that comes into the box, not the one on the control. No, dude, you may find something, but as long as the controller says off, those lights will never come on. Right. And I realized the disconnect. I taught them the piece, but I didn't teach them the whole solution. Right. So when we think about electricity and problems, understand it's not just the widget. It's not, and quit guessing. Next time, one of these days, I'm going to go to jail because one of these days, one of you guys are going to start to guess. I'm going to hit you in the back of the head. It'll be a small person, not a big kid, because they'll beat me up. But make the connection. What the problem was, it was an easy one. The case gets a signal for the lights from the building control system, and it has to get a signal from there to turn it off. You need to understand what's in your store. And if we weren't there, I wonder how many days they would have spent trying to figure out. But the controller said off. The controller told us what the problem was. We didn't listen. We didn't listen to our components. All right. And so I hate to preach. You know me, I get a little preachy.
Love it. So, that's the thing, though. It's like refrigeration is facts. Electrical is facts. There's no assuming. When I learned that, it took me a long time, being in the field for a long time and supermarket application, construction, service, startup. When I learned that, I started to learn that do not assume in refrigeration, find the facts out. That was when the game changed for me. It's facts.
I promise you this, gentlemen and ladies, once the light comes on with electricity, it is one of the coolest endorphin rushes that you're going to get. It just is. And so I encourage you to stay on it, study it, read the wiring diagrams, and rock on.
And this is what we do here at Refrigeration Mentors, bringing the experts from all around the world. Rusty from NSARC. Like I said, this is what we want to do. We want to uplift the industry. We want to help you become better and share this knowledge. So what we're just talked with you about here, I want you to go out and start training this stuff with somebody on your team, somebody you know. Talk to your wife or spouse or your husband about it, whatever. Start talking about this more. Get into these wiring diagrams, just like Rusty. Me and Rusty have done this dozens and dozens and hundreds of times, and we're still learning. we're still learning about this. Now we want you guys to do that too. Rusty, I want to thank you so much for taking the time. How can people find out a little bit more about you, where they can find you?
You can find us on NASRC's website, or you can email me at rusty.walker@nasrc.org, and check on our website. We have training summits going all over, and we do come out and do training. But we encourage you. I know Trevor spoke, and we're really happy when he comes out at our different training summits. We got one anybody in the West. We have one in Seattle next week, and I encourage you guys to come and visit us. Let's and let's quit. Can I give one more plug? Quit saying HVAC and R. That's not how it's supposed to be pronounced. It's pronounced R/HVAC.
No, it's not. It's pronounced refrigeration. Drop the mic.
Mike, yeah.
I love it, Rusty. And like Rusty said, get out to more trainings. You're here learning today. Tomorrow, get another training. Next week, we got to continue to learn. This is what it's all about. Continuing education, uplifting the industry. Thank you so much, everyone. And I look forward to seeing you at the next CO2 Experts Live. See y'all.